So I'm Matt Sylvester. I'm the corrosion control engineer for the lead and copper unit. I'm going to be covering the water main installation session here today, as well as a few others on Wednesday and Thursday. So this is a little bit longer of a presentation, so I'll try and keep it, as quick as I can here. So here we go. Here we are. Okay, so just as a general overview, this is mainly focused around water mains and the installation of them, but there's a lot more going on here, and I'll cover some of these things that go along rather than just direct installation portions of this. So we're going to cover some joints, water main material, the installation process itself, part of the permitting process, as well as project management and or doing the pressure testing and bacteriological testing. So this presentation, as I said, kind of covers quite a bit. So I'll try and keep it as entertaining as possible. So first things first, distribution system. What is the purpose of a distribution system? And essentially, it's just to transport the water from whatever the source is, or from a treatment plant, something like that, to the customers. As Martin was just talking in his first presentation, back in the day, maybe they were taking that just from a straight raw water source that we would consider today and delivering it right to their, relatively their customers, or to their, city center or whatever, to some fountain somewhere. Nowadays, obviously, that's a little different. We're now treating that water. We have that requirement, obviously, unless it's direct well water that maybe doesn't need treatment. But even at that, we are still now delivering this directly to the customers via, water mains and then, service lines themselves directly to the homes or the businesses or things like that. Okay. One thing to note, with distribution systems is that they're typically the largest single capital cost for any given community. The amount of water main that goes in the ground, the miles and hundreds of feet of water main that goes into the ground, and valves and hydrants and all these things really can add up. It's very expensive. So we want to be sure that we are paying attention to it, even though it's below grade. We're not typically looking at it. We're maintaining that distribution system as best as possible, right? So a little bit of, focus will be on that as well as we go through this distribution short course in general. So one of the biggest challenges to overcome, again, as I said, and Martin kind of discussed, you have the origin of water where it's this raw water. Now we are treating it, but even though you're treating it, there can still be issues in ways that water can get contaminated down the line. So that kind of brings us to that fourth bullet point there. What is the number one thing that preserves water system safety? And some might say chlorine and things like that, or corrosion control treatment, maybe something like that. But the biggest thing, believe it or not, is pressure. Okay, maintaining a constant, adequate amount of pressure in a system is crucial. That's how we, keep things out and keep the water in place and delivering it properly to those customers. So making sure we always have that constant amount of pressure. So as I said, it's that distribution systems cost quite a bit. It's that high capital costs. But what are the components? What are the things that break down a distribution system? Okay, so as the bullet points say there, number one off the bat, you have typically you'll have transmission mains. We would typically consider that something like 12 inches or larger. Obviously, that can vary depending on the size and scale of your communities. You also have just standard issue distribution mains. Maybe common day, we're probably typically talking 6 or 8 inch mains. Obviously there's still some historical, water mains out there, common one is like 4-inch cast iron. Some might have, those circulating mains that are, 2 to 4 inches, something like that are throughout the distribution system that we'd also probably consider distribution mains, although it's not probably typical common practice these days. Okay. In addition to that, we have storage tanks, right? You're coming from the source water itself through the treatment plant, and then instead of just having it pumped straight into the distribution system. We're having it go to some sort of storage facility, whether it's elevated storage tanks, groundwater storage tanks, where then it would need some sort of a booster pump or something to maintain pressure throughout the system. Okay. In addition to those things, those are kind of the main items. We obviously have valves and hydrants, booster pumps that I mentioned, service lines, and various other components. Okay, so there's a lot that's going on, and this is often a difficult point to, especially when you're talking, capital improvements and things like that, asset management. There's a lot of money here that people don't necessarily see. Your village board or your city council might not see these things. But there's a lot of money that goes into them. So it's always important to make sure that you're driving that point home, like, hey, we need to update these things, or we need to maintain them. Okay, so there's a lot going on that's not always seen with the distribution system. So these are kind of just general common system layouts. On the left here, you have that grid or looped system. Typically has that, kind of outer areas, that transmission main that's delivering high volumes of water. And then that internal portion that's kind of gridded out, right, is those distribution mains. And that's where the actual water is being delivered, essentially to the customers. So off of those distribution mains, and you typically have, your service lines and things like that actually go to the direct homes. But again, large amounts of water going through the transmission mains, and then kind of starting to get delivered to those individual areas via distribution mains. And then the other side of that right side there, is that branching or tree system. Typically we, at least from a Michigan perspective, we try to avoid this because, unlike the grid looped pattern, you're talking circular rotation of water. You're always kind of getting fresh water moving. It's not staying stagnant. The branching or tree system is not really like that. Okay, so you're having those dead ends there. And if you're not having, if say your distribution mains are there, slightly oversized or something like that, you have this stagnant water that's sitting there for a long period of time. It can lead to all sorts of things, whether that's biological growth, just aesthetic water quality, in general, as well as you can start having, corrosion issues as well. Deposits and sediment, dropping out, and making those distribution mains fail faster, things like that. Now, what I will say, in general, most systems, most communities do not have just one or the other. They're usually pretty balanced. It's something in between, maybe a combination of these things. So not everything's going to be looped. There probably is some dead ends in your system, but for the majority of time, you're talking, pretty decent layout of flow and consistent fresh water getting brought into the system. Okay. So, as I was kind of just alluding to on that previous slide, you have this opportunity for, especially if it's, something is inadequately sized, water mains are oversized or undersized for a given system. You have this potential for stagnation and potential aesthetic, as well as maybe even health concerns, depending on the situation, right? If too much water is sitting there for too long. So this is just kind of getting you kind of into that calculation mindset that, hey, there's a big difference here between just even something as simple as a 6-inch pipe to an 8-inch pipe. So as you're going through and doing these water main projects, make sure you keep these things in the back of your mind. Okay, so as you can kind of see here, that 6-inch pipe, 6-inch diameter, water main on the left is, roughly 28 square inches in area, and then that 8 inches is 50. So just by increasing that diameter by 2 inches, you're nearly doubling the amount of area of that piping material, or of that internal piping. Okay. And this next slide kind of drives that point home even farther, in terms of just actual volume. So what is area really? It doesn't mean a whole lot to us until we start talking about actual length of pipe and how much water is actually sitting there. Okay. So as we got from that previous slide, we got 28-inch square inches and versus 50 square inches. Just a little bit of conversion there. You have that 1,000 foot as it's specified there. And so we can go along here. So you're talking about roughly 1,500 gallons are sitting in 1,000 feet of 6-inch water main. Okay. And then versus that, again, maybe just shy of double, but 2,600 gallons are sitting in an 8-inch, water main with 1,000 feet. So pretty big gap, pretty big jump in volume there that you're talking when you have these two different size water mains. Okay, so making sure that your system is adequately sized and you're not having this large amount of volume sitting there becoming stagnant. So getting into water main materials, obviously there's a lot of historical aspects to this as well as current day aspects to this. So these are the general materials that we're looking at. So you have cast iron, you have ductile iron, asbestos cement, you have plastic, but you have multiple different versions of plastic. So you have polyvinyl chloride as well as molecularly oriented PVC. Okay, and then you have HDPE, which is your high density polyethylene. You also have steel and concrete. So all these materials are all potential viable things that might exist in your distribution system. So you should be fairly familiar with what might exist or does exist. Now, what comes along with each one of these pipe materials is making sure that they're properly approved, right? So one of your big ones is you're making sure that it's meeting that NSF 61 standard, right? In addition to this, when we're talking about plastic piping, whether it's PVC, HDPE, whatever the circumstance, making sure that it has that NSF PW indicator on it, like it shows in that right slide there. So what that PW stands for is just potable water. Okay, and basically what that stamp is saying that yes, this meets your NSF ANSI 61 certification. Okay, pretty straightforward. So selecting the proper water main material, there's lots of things that go into getting the proper material that fits your system. Okay, and so obviously there's this whole list here: compatibility of existing materials, the actual strength of the piping itself, whether that's stress or crushing, strengths, the internal smoothness or the C factor is what we typically describe that. Okay. Resistance to corrosion, both interior and exterior, I'd argue that resistance to corrosion. The storage and handling of those water mains, ease of tapping for that corporation fitting, and then conductivity. So that's for the locating or potentially thawing aspects of that. So if you're putting in a PVC, pipe, water main there, you're going to want to, what is it, 14 gauge, if I'm not mistaken, your tracer wire along with that, so you can then later track that pipe down, know exactly where it's at, located. And then obviously permeation of VOCs, volatile organic compounds. And then what comes along with that is making sure that they have special, gaskets, making sure it's the proper grades and things like that. If that's Vital or whatever's necessary for that given contamination in that area. Okay. Now, one thing you might have noticed that's not on this list, and for decent reason, although it is important, is cost. Cost was left out of this list because that should be your last consideration. Okay. There's a lot of other things that go into selecting your water main material where cost should not be that factor. Okay. Maybe in a lot of circumstances that some of these things won't matter in your given community. So maybe a cheaper option is better, but you need to make sure that you are checking these boxes first before you start considering that cost option. Okay. So as we kind of talked, as I just mentioned a couple slides ago, with the different water main material, and one of the ones that was left off was wood. Obviously this goes into the historical aspects of this. I don't believe at this point in time any of these are still in existence that are actually in operation, I should say, because from time to time, we'll hear about a community still digging some of these up. I'm not going to say a whole lot to this outside of that. It's just kind of an interesting fact that we used to do this, just another example of how we, distributed water and the importance of it, that we stressed on it then, and even more so now that we're making these strides and improvements in water main material. Okay. Another older material, but this is actually still commonly in use, is gray cast iron pipe. Okay, this is probably the oldest material that's going to be in about any water systems, distribution systems. They can be upwards of 100+ years, depending on the situation. These might also be, to some extent, the bane of some operators' existence, right? How many times have you had a, aesthetic water quality complaint for red water or something like that? And it turns out that that system is connected via, 4-inch, cast iron main. So that house is just getting this, high deposits of iron that are coming off that, unlined cast iron. Okay. So, so the majority of that cast iron, as it says there, is unlined. So that leads to that corrosion, those deposits, tubercles, things like that. Again, typically leading you to, poor aesthetic water quality. The cast iron was superseded by ductile iron, which we'll talk about in a moment. And then there's an AWWA standard for C106. Okay. Cast iron, and we're going to kind of walk through different, material types and kind of just talk about, relative advantages, disadvantages here. So this is kind of a common trend. We'll kind of cover a similar slide for each material here. So advantages, it has a good history, a long life. Like I said, there's 100+ years for some communities. They've lasted a very long time. Because of that, the reason for that is that they have high bursting, crushing strengths. They're very durable material. They're fairly decent to corrosion resistance, at least, to some extent, they'll stand up. Although there is tuberculation, there is probably, especially with the unlined portion of that, red water complaints and things like that, but they relatively hold up pretty well. They have a medium initial internal C. Now note that initial portion of that, because as I've already mentioned, that C will deteriorate over time. And that's actually in the disadvantages column, right? So those tubercles, those things like that make that volume or that flow, decrease over time. But they are conductive, so you can track them down. So you won't need a trace wire or anything like that. They're easy and you can have direct tapping. Pretty straightforward with those. They're not permeable to VOC, so that's also positive. And then they're generally fairly easy to repair. Now, some disadvantages with that, obviously they're no longer available, so you're not going to be able to do, just a straight replacement of cast iron to cast iron. They're extremely heavy material. As I said, that C deteriorates over time, so that C effect, that roughness will get worse and worse. And then, as it is for most situations for Watermain, you'll need a special gasket when you're going through, certain contaminated areas. Despite having high bursting and crushing strength, there is that factor that they can have beam breaks. So that's a straight crack across that water main, because they're very, very susceptible to that shearing. Okay. And then they're also conductive. So this is kind of another aspect. If hopefully nobody's doing that anymore, but theoretically, if you were, in the winter time, things like that, if you were to try and hook a service line or something like that, up to a welder or something to thaw a service line, or if you have, electrical current nearby in any capacity, that can be, hazardous later down the line. Okay. So corrosion conductivity, again, unlined cast, we've already kind of talked about this. Tubercles easily formed in those. You can have that, rust factor and things like that, leading to aesthetic water quality complaints, as well as you can actually have, decrease in flow, especially if it's a, 4-inch cast iron or less. There's that likelihood that you're going to be losing that volume there. And you're no longer delivering that amount of water and or pressure to a given household, to the residents, right? Okay, so things to keep in mind, especially if your system was not, has a history of not being maintained well. So the superseded portion of this, so cast iron, eventually rolled into ductile iron, which is a more consistent form of cast iron, as well as, has some difference in its manufacturing to make it less, brittle, a little bit more flexible, ductile in general, So it's not going to have that same kind of shearing aspect that cast iron might have. Okay. So very popular in Michigan, very popular, I'd say nationwide, but especially in Michigan. We've kind of overcome that interior corrosion kind of concern because there's now, cement mortar lining. You're not going to have those same aesthetic water quality complaints later down the line. That C factor might stay together a little bit longer. So that's, very, very good. As well as you have exterior, epoxy coating. You also have zinc exterior coating, and then there's, you can always have it wrapped in polyethylene as you're putting it in. So as this kind of, just alluded to, that's an example of a polyethylene wrap, whether that's going through, contaminated soils or whatever the reason is for, some systems even just say that it's easier to put that in the ground, actually put the installation together because it slides easier and things like that. But better external, protection in general. So that's basically just a sleeve and it just slides over that water main. Okay. Another example, as I just mentioned, kind of that zinc embedded external coating, again, just kind of protects it from a corrosive environment in whatever that is. So zinc is a sacrificial anode in these circumstances. So you're not having that same kind of breakdown of that material. Okay, you're not having a corrosion factor, at least on the external side of the piping. So ductile iron, just keep going into it. So common diameters, 4-inch to 64-inch. Standard lengths, it kind of depends, but typically you're talking probably 18 feet is your typical, stick length. Max working pressure is about 350 PSI. Now, those classes can change for pressure. So it's always good to make sure that you know what you're purchasing, know what you're putting in the ground, make sure those classes meet the PSI that you'll need. Okay. And in addition to that, make sure that you're meeting the AWWA standards for ductile iron. That's C150 and C151. And then there's obviously multiple different styles of joints that go along with ductile iron. Push-on joints, mechanical, flanged, restrained, flex ball. That's just typically for your river crossing portion of that. So again, this is advantages, disadvantages. So strong and durable. Has better flexing than that cast iron, especially. Good corrosion resistance, both internal and external for the most part. So it depends, on what you're actually purchasing. But usually it's just a better overall material than your cast iron. It has a high internal C, and it doesn't have, because of that, mortar lining or whatever the internal lining that you might have, it's typically going to stay that way. It's not going to change all that much over the time. Okay. Also conductive, it taps easily. It's not permeable to VOCs, and as well, it has a good history. It's been around for, quite a while now, but it's, pretty standard method, pretty standard, option for materials. Disadvantages, obviously it's still iron, so it's still heavy. Maybe you do need to buy some protective wraps or some cathodic protection, that zinc coating, to protect against corrosive soils. But those are still an option. So it's kind of that toss up between advantages, disadvantages, depending, right? Obviously, again, you still need gaskets if it is going through that contaminated area. Okay. And then you got to be careful, a little bit more careful, because there is that mortar lining. And so you don't want to break that loose and then cause, additional issues later on. Another pipe material here, we got PVC, polyvinyl chloride, also a very common pipe material in Michigan here. One of these things you got to meet, and I think we already kind of discussed this, but meeting certain standards. So NSF 14, NSF 61, those are the big ones that you're going to be paying attention to. But if it has that NSF PW or potable water stamp, that basically means that it's meeting both of those standards. Okay. One of the things, unique with PVC and plastic pipe in general is basically making it that, or is that SDR, standard dimension ratio. And so it must be, in this case, 21 or less. And we'll dive into what SDR means in a little bit, but essentially it's that comparison between the actual diameter of the pipe and the pipe wall thickness itself. So when those things change, whether it's plus or minus, whatever you're talking, that's going to be affecting that pressure classification. Okay, so again, just something to keep in mind as you're selecting pipe material, putting stuff in the ground. Okay, and then because this is not conductive, you're going to need a tracer wire, as I had mentioned early on. So PVC, these are kind of your common diameters. They're 4-inch to 48-inch. Standard lengths varies, but typically you're talking about 20 feet is probably the most common. Max working pressure there is that 200 psi, so a little bit less than we just talked about for that ductile iron and cast iron as well. Those are your two standards there, AWWA standards, C900 for those certain sizes, and then C905 for the little bit larger Watermain selections. And then you have a couple different joints there as well. Push on, restrained, and mechanical are your primary joints. So advantages, disadvantages to PVC. So it's lightweight, corrosion resistance, both internal and external. Okay, is a very high internal C, so that's very smooth interior, and it's really not going to probably be affected over the years. It's a good alternative to metal, especially if metal prices increase and things like that. Not that cost is everything, but it is still something to keep in mind. But it also has a good history, right? It's been around for quite a while now as well. It's good material. Everybody, for the most part, has some form of PVC in their system, and it holds up. High impact strength as well. So some of the disadvantages to it can be damaged by sunlight. So if you're leaving it out for a long time, leaving it out over summer because you had it for a Watermain project, you bought a whole bunch of it, and there's some left over, there's that potential it could break down and deteriorate. Okay, because it's just plastic. Plastics break down, especially with sunlight and temperature and time and everything else, right? So requires careful handling and bedding. So again, it can have that stress fractures and things like that. So making sure that you're handling it properly, not damaging it in certain ways. Pay attention to that. They can be somewhat susceptible to VOC contamination, so that can make it a little bit more difficult, especially if you're in a highly contaminated area. One additional thing to consider. Again, as we just talked about, it's not conductive, so you got to keep that tracer wire going so you can locate it later down the line. And then it can be tapped directly, but saddles are probably recommended in most situations. Okay, going to be more durable, going to stand up over time, so you're not having an issue with your corporation fitting. So fusible PVC is also another option. And this kind of goes into a similar kind of concept to HDPE, even though they are different. So PVC pipe can also be fused together. So it's not necessarily just a push-on joint or whatever the situation there. Has lower rates of expansion and contraction than HDPE. So again, it is slightly different, but this is just another example of it. So these have I believe that is one different AWWA standard there. C900 is the same, but I believe C906 is different. If I recall correctly, I think that was C905. But yeah, so just another example of potential there for PVC. Now getting into HDPE, the high density polyethylene. These are, fairly robust. They can be very thick, strong materials. That's why they're typically very good for, river crossings, railroad crossings, highway crossings, things like that. They can withstand some of those, and they can be, a thicker material typically. These are also joined by thermal fusion, as that PVC portion was before. So basically what that means, and I think I'll dive into a little bit of an example of that, but basically thermal fusion is you're heating two ends of a PVC, two sticks, you're heating the ends of that, and that's what you can see that the bottom right corner here in that picture, and then you're basically going to be forcing them together until they, all intents and purposes, they stick together and they have a pretty strong bond. You're actually pushing those materials so they're now connected, right? So those have their own NSF standards, 14 and 61 as well, same as the PVC. They have a much lower SDR, so that would mean that they're typically a stronger material or requires, different kind of concept there, or different kind of pressure rating that goes into that. And again, we'll dive into SDR in a moment. And then they have high rates of contraction, expansion. Open ends need to be anchored. Okay, and we'll talk about that a little bit more in a moment. So HDPE, common diameters, it can go 4" to 63". So a little bit more variability than your PVC typically. Standard lengths theoretically can be, unlimited. Although your common sticks are going to be, typically in that 18 to 20 feet. But, obviously from that thermal fusion, you can make them as long as you want, right? So that's, kind of can be a perk, I suppose, can be that advantage. Max working pressures is 250 PSI. So that's, pretty solid for most circumstances. It has that 906 AWWA standard, similar to that fusible PVC that we just mentioned. But that's for all extents of it, so 4" to 63". And then basically they have two forms of joints, so that thermal fused, and then they also have the mechanical methods as well. So this is getting into that anchoring of the ends portion of this. This is an example of what would happen, or how it should be determined if you have HDPE going to a ductile iron water main. And so ductile iron's on the left here. Your HDPE is on the right. You can see, let me get my cursor over here. You have, some rods here, some bars here for that mechanical restraint. We'll talk about thrust restraint in a little bit and in some more detail. You had to fuse their joint together. I think this is actually, this is a restraint saddle as well to kind of help that thrust restraint. You have the thermal joint here that connects the actual HDPE mechanical joint adapter. The mechanical joint adapter essentially here is what is, and again, we'll talk about this in more detail, but it's basically just holding this gasket in place. Okay, so going from bell and spigot end, obviously you can't thermally weld plastic to ductile iron, so you have to have this connector piece here, this adapter, and then have it mechanically restrained to keep that joint together, keep that gasket in place. Okay. Right. So advantages, disadvantages. HDPE is fairly lightweight. Its corrosion resistance is very good, both internal and external. Obviously, it has high internal C, so it's very smooth, similar to the HDPE, or similar to the PVC, I should say. It's fairly flexible, which is commonly considered a good thing. And then, can be installed by directional boring. So, less restoration needed involved with that. So, you're not tearing up somebody's yard. You're not doing some trench excavations. It's, fairly minimalistic. And then can use ductile iron fittings if necessary. Okay. As we just showed on that previous slide. So disadvantages there, higher levels of installation skills required. Again, it kind of goes into, depending on what you're doing, having that thermal welding, that's an additional piece of equipment and knowledge and things like that go into that. But can be very crucial if you are doing, under a highway or under a railroad or things like that are a beneficial thing to have. Unfortunately, they are highly permeable to VOCs. That's not ideal. They're non-conductive, so you'll need that tracer wire. Taps and fittings must be electrofused because, again, it's just basically a stick of pipe. There's no spigot and bell end like you would typically see. There's high rates of expansion and contraction, which can come with their own whole series of issues. And then open ends and mechanical joint adapters to other types of pipes. So if you don't have a bunch of HDPE, which is probably pretty common, you're going to be going to another pipe material. You got to make sure that there's mechanical joint adapters and things like that to keep those pipes and those gaskets in place. So as we had discussed a little bit earlier, we're getting to that SDR, right? That standard dimension ratio kind of concept. So as I had kind of mentioned, this kind of just helps with that pressure classification and things like that. And essentially, it's just a ratio. The SDR is just a ratio of the outside diameter over the wall thickness. Okay, so that D, the outer diameter of the pipe, water main, and then the S is the actual thickness of the pipe material. Okay, so higher the SDR means thinner wall, lower pressure rating. Lower SDR means thicker wall, higher pressure rating. Okay, so when we go from that 21 to an 11, that 11 is going to hold up a lot better in terms of pressure standards than that 21 that we discussed. Okay. Again, just things to keep in mind as you're going through that water main selection and things like that. So steel is another option, used in water systems in the USA since 1852, so it's been around for a while. Above grade installation, typically you'll see them in plants or pump stations, et cetera, can withstand almost any pressure. They can be made fairly customizably. Walls made to any thickness, high pressure area. They can be fairly customizable in that front. Both interior and exterior must be protected from corrosion because they can be susceptible to that. So certain precautions need to be made. Advantages, disadvantages. So high tensile strength, good choice where some movement may occur. They can be flexible if or they can be good for withstanding those pressures when necessary, things like that. High internal C, so again, fairly smooth, maybe not as much as your HDPE or PVC, but again, fairly smooth relative to that. Moderately lightweight, it's kind of proportional, so that's somewhat dependent, but relatively, it's probably going to be more lightweight than your ductile iron pipe and cast iron pipes and things like that. Are conductive, obviously they're metal as well. Disadvantages, flexible, requires good support and bedding. So as you're putting them in the ground or whatever the situation is, or if you're having them in your water plant, making sure that they have that support, so they're not flexing too much and maybe disturbing the joints themselves, or maybe even bending a little bit, causing a thrust issue later on. So poor internal and external corrosion resistance. So again, you got to keep those things in mind, whether that's painting the exterior or something like that, or having them lined on the interior. All things to consider as you're going through that. And then specialized fittings and repairs. So again, because they're customizable, it would also require them to be a customizable part or customizable fitting, or a direct replacement might be more difficult to come by depending on the situation. Another example of pipe material here is concrete piping. This is typically used for large diameter transmission lines. Combine steel and concrete to produce a very strong corrosion resistant pipe. So these are typically when you're talking very large diameters, that's bringing a lot of volume of water to the area. Maybe not your individual distribution mains, but your transmission mains themselves. So concrete, here's some advantages, disadvantages. Again, strength, obviously, especially when they're reinforced with steel and things like that. So they have high crush resistance, high impact resistance, things like that. They're corrosion resistant because they're not really talking metal. Fairly high internal C. Again, maybe not as high as your PVC or your HDPE, but relatively pretty high. Not permeable to VOCs, which is always positive, but per usual needs a special gasket for contaminated areas. Excellent choice for large diameter pipes, and obviously has a very good history. Disadvantages here, it's obviously very heavy. It's concrete. It's gonna weigh quite a bit. Requires careful handling, as well as the installation process is going to be much more difficult. In terms of that, you're going to need special equipment, things like that. They're not easily tapped, although they're usually not really meant to be tapped. because you're not putting a individual house right off of the, 64-inch concrete main, or, 10-foot concrete main or something like that. So it's a little different. They can be the largest diameters. Now, what comes from this, although largest diameters itself is not a disadvantage, it just means that they're not always in stock and they might be a special order. So they can be moderately customizable, but that doesn't mean that they're around if it's not, a standard use. I have a very good example of this. In early August, GLWA had a large main break that I'm sure everyone's aware of. It was all over the news. That was a 10-foot diameter pipe right outside their plant, basically 10-foot diameter pipe. At one point in time, from what I was informed, all the pieces that were 10-foot diameter concrete piping was in the state of Michigan, helping that, situation out. So, we were fortunate enough that there was enough that existed, but we also had to, ship. I believe one of them was coming up from Texas, if I'm not mistaken, one of the sticks of pipe. So it's, they're not just on order, they're not just on standby, I should say. They are highly customizable, and they'll probably also cost a pretty penny as well. So things to consider. So water main joints, desirable features that come from water main joints. They got to be non-toxic, don't add to taste and odor issues. They have to be fairly elastic, high strength, workability, availability, and they got to be obviously economic. Okay. So here's a few joint types that we've already kind of briefly mentioned or discussed. So bell and spigot, that's your typical push-on joint. You have, I think most people are fairly familiar with this, and we'll talk about this, but bell end is kind of that rounded end, and that spigot end is like a typical end of a pipe, right? It's straight and linear, and it slides into that bell end portion of that. Now, in the old school cast iron, you might even have some lead caulk joints. That's maybe around that 1945 area, where, it's actually, packed in there. So that's kind of a unique situation. I don't think there's too many that I know of. I know of maybe 2, possibly 3 communities that still have those in their system. So it's fairly unique these days. Flange joints basically just means that it's bolted together with a gasket in between. It's a fairly rigid joint. It's not much for, not meant for much flexion or anything like that, like a bell and spigot might allow. Mechanical joint, or MJ joint, or MJ, I should say, used on bell and spigot pipes, right? They're bolted with a gasket and retaining ring. Please note the mechanical joints are not meant for containing thrust, okay? The mechanical joint, the purpose of that is to basically just keep that gasket in place, okay, when you're going into that those two different, pipe ends. The restrained MJ joint, though, does contain thrust. So keep that distinction in mind. So there's mechanical joint, or an MJ, and then there's a restrained MJ, a restrained mechanical joint. That does contain thrust to some extent, and that will keep those pipes together, holding those together, not just necessarily focused on holding the gasket itself. Okay, and then as we had mentioned with PVC and the HDPE, there's also fused joints. So these are common examples of a flanged a joint. This is ductile iron pipe here. All of those portions. Let me get my cursor over here. All of these here with the you have your bolts and your nuts here, and if you can't really tell, but that line in the middle is essentially going to be your gasket that's being held together. Just as this is shown here, bolt, nut going through the two ends of the piping, and then you have this gasket here that keeps the water inside the pipe. Okay. Notice they are fairly rigid pipe joints there. So restrained versus unrestrained, as I just kind of went into a little bit of detail there. You're talking, this situation where you're holding the pipe together, trying to maintain that thrust restraint to some extent, keeping the pipe held together. That's the restrained portion of that, where the unrestrained portion, that mechanical joint, is just holding that gasket in place. So as you can kind of see down here, this is not actually trying to hold the pipe at all together. It's just pushing that gasket tight into that groove there, making sure that water stays put. Okay. And we're going to get into, thrust restraint a bit. So as we go into, connecting water mains and things like this and making changes and moving it about your system, there's lots of things that go into that, lots of fittings and different characteristics that the water main needs to do throughout your system to get it to certain areas. So whether that means there's the, a T up here, or reducers or increasers as well, whether it's a dead end that needs a cap on the end of it, whether it's a closed valve itself, whether it's, a Y here, thrust is a big deal, and it's not oftenly, maybe focused on, because you're, looking at other things, making sure, the fitting's proper and things like that, but thrust is very important. So that thrust has to go somewhere. So we don't want that joint to pull out or have some disturbance there. We need to make sure that that joint stays together. And so maintaining good restraint on whatever direction that thrust will be in is crucial. Okay. And so the next few slides is going to be kind of addressing that. So it's all about the soil. As it just mentions there, a big aspect of this is making sure that that is, unaffected, touched soil on the other side of that. So you have a big thrust block up here, but maybe there is some soil removal here. The biggest thing is just that soil isn't going anywhere. So that thrust block has something to disperse all that energy into. So as you come up, as the water is going to come up, as it shows here, and it's going to make this 90 here. A lot of that thrust is going right into that block, but that block isn't going to do a whole lot if it's not, on solid soil and distributes that force into the soil. Okay. And that highly compacted, fairly untouched soil. So this is, another, example of an opportunity of what you can do. And this is kind of a common theme here, is that there's maybe not necessarily any there's wrong answers to this, but there's multiple different right answers to this. Okay, so you can come up with different ways to restrain and adequately control these thrust situations. So utilizing that soil pressure, again, having that undisturbed soil. If you don't necessarily have thrust blocks, although it's highly recommended, there's ways around that. So you need to make sure that all of that thrust force is accounted for. So in that situation, pretty much you're talking about the, extending that water main as long as possible. So all that force is being distributed along that main. Okay, so it's not just on one point, and this is all loose soil where these joints can be affected. Okay. So again, mechanical joints. This is a good, kind of overview of it. This bolt and nut situation here with the bell and spigot end, it is not really touching, this water main portion here, but rather that is pushing down directly on this gasket. Okay. So it does not restrain thrust. It merely just holds that gasket, in place, basically, just to make sure that there's good, adequate seal going on. This is very different from a restrained mechanical joint. Okay, so as you can see here, this is actually, being driven down into this point. Yes, it is also holding a joint in place, or holding a gasket in place, but it is pinching along this pipe wall and creating a nice tight seal, and does contain some thrust. Maybe not all, depends on the situation, but it does contain a large amount of thrust. Okay, an example of this, real life example of this, is what we typically, this is a brand name, but Mega Lug. Okay, so what's actually occurring here, as you can see, this is, that adapter piece there, and you can see these kind of, fairly sharp teeth that will end up biting into that pipe wall that will slide through this middle here. And if you notice here, you're gonna, put your wrench on the end of that, and you're gonna torque it down. And once it gets to whatever the correct amount of torque, this head will actually shear off. So with a restrained mechanical joint, maybe they're not permanent, but they're pretty close to it, right? You're going to have a heck of a time getting that back off once it's there. And that's the intent, right? You don't want that going anywhere. You want that restraint to be completely resolved. Okay. Okay, so design of restraining system. So again, different methods here that go along with this. There's maybe not necessarily just one right way, but there are wrong ways. But some of these aspects here, again, thrust blocks, restrained mechanical joints, restrained push-on joints, depending on what the situation, it can be adequate, or you might need to use multiple depending on the situation. What you might notice as you go through this process of whatever Watermain project that you're doing, trying to restrain this, you're not going to really find specific wording, from AWWA specifications. You're not going to necessarily find it from 10 state standard. You're probably not going to really find it in Act 399 or anything like that. But it is still important to focus on, because again, there is right ways and then there is wrong ways. There's multiple different right ways. So there's not necessarily one, perfect way to do it, but there are wrong ways to do it. So you got to make sure that you're the one that's designing this, that's a professional engineer, whether that's your contractor or your city engineer or whatever the circumstance, make sure that they're doing it properly, make sure that thrust is completely, accounted for. So now some additional things that kind of, can help with this, or things to consider that will help with this, distributing that thrust is, well, I'll just basically point out that DIPRA is a great source of material here. They have a lot of material, a lot of educational material, as well as, online, graphs and charts and tables, as well as even calculators. And I think I'll talk about one of them in a minute. I don't remember if I included it or not, but things to consider as you're going through the design of restraining that thrust. So soil types, pipe sizes, pipe materials, water flow, obviously directional is probably a big portion of that, and then working pressure. Okay. All these things to consider. And again, there is material out there to help you through that process. So, this is an MJ fitting or example of it. Typically a restrained mechanical joint will only be used when needed, because typically it's more expensive. Okay. Second, a flange connection can be more easily taken apart, not so with mechanical fitting. Okay. So that's kind of what I was just talking about, especially with those restrained joints. Once it's there, it's not really going to come apart, very easily like you would with a, flange connection or something like that. Okay. So some more joints that are, options you have, welded, whether that's metallic or non-metallic, whether it's using solvent or thermal welding that we discussed. Then you also have sleeve couplings, whether that's threaded, non-threaded, or dresser type coupling. And dresser is also a brand name, and we'll talk about that. This is typically a slip joint is what you consider this, but dresser is actually a brand name. It's commonly used, right? Like Kleenex or something, So this is an example of that slip coupling. Essentially what you're doing here, and what you can kind of see from this picture, I think here best, in my opinion, is you have you have a pipe here and a pipe here that are connected, and maybe there's a gap. Okay. And that gap isn't necessarily connected. You can't force these together. It's maybe not a perfect bell and spigot kind of situation. So you're trying to connect it with this slip joint. So the slip joint is going to come over the top, in between the two, and then it's going to form. So this, from this picture down here, you have the actual, portion here that would be this here, the top and the bottom. Obviously this is just a plan view of this, so it's a little different. And then you have the joint, the gasket portions of this that are held together by that bolt. So that's this part, this part, this part, and this part. Okay. And again, that kind of just keeps all that in, keeps the water together, despite having, maybe not a direct connected, joint there between the two water mains. Now, push-on joints, these are pretty straightforward. I think everybody's probably worked with these to some extent. Bell and spigot, these are simple. They're, probably the cheapest of the bunch. Obviously, you're going to have to, do a gasket portion of it. There's going to be a gasket. You're going to have to use, probably some sort of a lube on there so that bell and spigot slides smoothly. As you can see in this picture here, you have kind of two lines here. These are just basically guidelines. So if you can still see that first line, you haven't pushed that spigot into that bell far enough. And if you can see the second line, you're probably, or if you can only see the second line, you're probably in pretty decent shape. Okay. So that's just an example. It's probably seated fully at that point. As I said, and we've discussed a few times already, gaskets, lots of different types of gaskets. I'm not going to walk you through each one. I'm probably not even familiar with, half of these, brands and different options that they carry. But the main idea is that gaskets can be selected for certain reasons, for certain, situations. And it's important to make sure that you're using the right ones for whatever that might be. So again, this kind of gets into the gasket material. Obviously, I'm sure there's lots of different brands that you can use, and then they have different, varieties off of that. So this is kind of just this hierarchy kind of concept. You have good to best. So that Viton, although it's costly, is going to be your most resistant to, things like solvents and things like that. And this is, Ductile Iron Pipe Research Association. This is just an example that they have put together for common uses there on the right. And then your different actual chemical makeup of whatever that, gasket style is. Okay. So depending on what it is, you have different maximum service temperatures, you have different, styles that might fit. So again, you're selecting though, you want to be selecting those gaskets based on whatever situation is necessary. Okay, so I have a break time available, or do we have time for that or no? Should I keep going through?
We are at about 10:26. We're more than halfway through the course. I think it might make a sense to do a 10-minute break. Give everybody an opportunity to get up and stretch and maybe go get a cup of coffee.
Okay. All right. Yeah, let me know when you want to start back up then.
Why don't we start back up at 10:37?
Sounds good.
And I'll go ahead and I'll put a timer up, and we'll go ahead and class will resume at 10:37.
Thank you.
Okay, Matt, 10 o'clock, 10:37 time is up while we're waiting for you to re-show your screen or our next speaker to re-show. We're going to do a poll question here.
Okay.
So I've got quite a few to choose from, but I'm going to do this one. And just to kind of get an idea how what type of experience or how long people have been working in the drinking water field. So if you want to take a moment to answer that, and we'll share these results after they compile. So this is our third poll question, and we will have one at the end of today's presentation as well. So don't take off just yet. If you're looking to get continuing education credits, make sure you do answer the poll questions. Okay, looks like we're having some people having some difficulty selecting the poll. Remember that Zoom does need to be your primary window. So if you are multitasking, bouncing between windows and that, just make sure that Zoom is your front and center window. And you should be able to see the poll. So it kind of looks like we've stalled out at about 87%, but the poll has been running for over 2 minutes. So I'm going to go ahead and close this poll and share the results. So Matt, it looks like the majority are 0 to 4 years with 49%, roughly about half of those that responded. And pretty even split the rest of the way, other than 15 to 20 years is below 10%.
Okay. Well, that's hopefully we're learning a lot during this short course then. That's good.
All right, if you want to take it away.
All right, so out of the break time, getting back into fittings, and I know we're maybe a little short on time probably, so I'll try and speed this along a little bit. But fittings just in general, and I think we've talked about this enough on a few different slides, but we have elbows at various degrees. You have side outlets, different types of elbows, right? You have T's, you have crosses, you have reducers and increasers, and then you have true Y's, and then standard Y's. Okay, and then there's obviously other different types of fittings as well. To go along with that, there's also fitting accessories. So flange spacers and adapters, you have blind flanges, you have caps and plugs, you have cutting in sleeves, you have flare fittings and elbows. Okay, and we'll talk about quite a few of these as we continue to go through here. So this is just kind of a standard issue, 90-degree elbow. There's not much, that you're probably not familiar with here, but there is just a, one little, quick question, quick quiz I want to throw at you. Right here, if you were to look at this elbow that we're looking at, would you call that a flange or mechanical joint? Okay, is it a flange or is it a mechanical joint for that 90-degree elbow? Well, that would actually be a mechanical joint. And one way to tell here is that you actually have this bell end. So you'd have that bell and spigot. So yes, there's, rivets here that you would, or holes there that you would put that bolt through. But if you recall, that flange portion would be pushing together a gasket in between those kind of portions. So it'd be kind of in here, rather than, having that bell end going into that, and then having that mechanical joint actually pushing into the gasket at this side. Okay. So this would actually be a mechanical joint, just to get you familiar, right? In a similar kind of situation here, these are reducers, or theoretically, I guess they could be, increasers, but most of the time you're talking about reducers here. You're pushing it, from water from this side, reducing it down to a smaller diameter over here, right? And so the same question could be asked, are these flange or these mechanical joints? So, maybe this gives away right here. You have that, again, that kind of that bell end, that would be mechanical joint. Same with this larger one back here. Hard to tell exactly, but I would, potentially here, I can't tell exactly if there's holes there, but that's a, potential there. And then these are just regular flange joints. There's no bell end. So that's just going to meet flat with another piece. And then that bolt, you can actually even almost see the point where a gasket was originally. That flat gasket would have been sitting there. Okay. So this is just kind of, again, get you real life examples of what's going on here. So you have a couple of blind flanges here. That's these, rounded domed cap things that are, basically reducing these down, reducing this 36-inch, concrete main that's over here and over here. And notice that they're actually rounded. That's basically just to prevent, direct stress in a certain way. It's minimizing that. So it, kind of, flows down in and reduces into this, 16-inch. So you have a mega flange here. So that's that really holding it together with a bunch of bolts here. It continues down. You have this 16-inch cross. Okay, so cross here. It can theoretically go this way as well, but that's capped off, as you can see. This looks like some form of a reducer as well. And it's, into that 12-inch there. So again, a lot is going on here. There's one additional thing that's actually slightly off camera. If you were to look right over to the right here, if we could pan the camera, pan this picture over, there's actually a large, concrete wall that's actually poured over here to help, restrain some of that thrust that we've talked about. Okay. So that's just a, example of a, real life situation. These are mechanical joints, caps, specifically. These are actually, as you can tell here, they're probably restrained. Obviously they should be, because there's gonna be a lot of thrust going to that end, right? So you got these screws going down that's gonna actually bite into that pipe wall itself, not just the cap itself sitting at the end that could easily, blow off if there's, excessive water hammer or something like that. This is another, kind of special type of fitting here. Basically, this was just used during a construction phase, used for, flushing and sampling portions. Again, kind of a cap here, but it has this ball valve at the end where you open it up and maybe blow off some water or take a sample from or whatever. You can also, if you look very closely, this is also obviously a mechanically restrained joint as well. Okay, so getting into permits, when is an Eagle permit required? Well, in general, I'm going to just, point you to Act 399, follow those guidelines as best as possible. But there are situations that are maybe a little less unclear. So we're going to do a couple, quick examples of those. So bullet point number 1, if we were to replace, okay, that's a big one, replace 80 feet of 12-inch main at an intersection reconstruction. Okay, does that need a permit? Well, I would say in general, no. You would not need a permit. Okay, so the reason I'm saying that is because one, it uses that word replace, so it's a direct replacement that I would consider. So it's a 12-inch main, probably of a similar material with another, similar 12-inch main. It's also only 80 feet, so it's kind of a smaller amount. pretty straightforward. You're not changing those capacities. You're not changing those flows. It's a direct replacement, 12-inch to 12-inch. Likely would not require a permit. Now, what I will say as a caveat to all of these, if you have questions, there's a few things here. Eagle, from the drinking water perspective, has free permits. So having a permit in place doesn't affect you. Maybe it adds a little bit of time or something to your project, but if you're planning enough ahead, it's really not going to be much of an issue. And obviously, if you have questions, you should absolutely contact your district engineer as you're going through this. So if you're kind of this in-between phase, but for the most part, if it's something fairly simple, it's not changing flows, it's not changing capacities, it's not changing, some large schematics of something, there's a potential that it might not need that permit. Okay, just like that first bullet point. So the second bullet point, install 80 feet of 12-inch main at an intersection reconstruction when it was previously an 8-inch water main. Okay, this would be one of those situations. You went from an 8-inch to now a 12-inch. That is changing the capacities. That is changing the flows. That is, affecting the general, hydraulics of the system. Okay, so then we would say yes, that would likely need a permit, right? You should absolutely send that one into Eagle. And then that last one there. So replace 80 feet of 4-inch main due to poor bedding conditions causing multiple breaks. So this is kind of a toss-up. I would, at least the notes here, my speaker notes here say no. Basically what it says here is this is an unwritten policy, 100 feet or less. So basically 5 sticks of pipe is considered maintenance and not like a replacement portion. Okay, so even though 4 inches is inadequately sized for systems with fire protection and capacity, is an issue. Okay, so though this might not necessarily need a permit, I would still probably recommend that you do go through Eagle, just because in most circumstances, I would argue that 4-inch water main is probably inadequately sized. Okay, so not everything's a slam dunk, and it doesn't hurt to reach out, and it doesn't hurt to submit a permit either. Again, they are free. Maybe it adds a little bit of time or something like that, but overall, highly recommend sending something like that in, or at least giving a call to your district engineer. Okay, so kind of those what ifs continued. These are getting into actual, different piping changes. So replacing a 400 gallon per minute brand X, doesn't matter, line shaft turbine pump with a 400 gallon per minute brand Y line shaft turbine pump. Okay, so does this need a permit? So I would say in general, no, it would not. You're pretty much changing a relatively similar replica with something else. That's 400 gallon per minute. The capacity is really not changing at all. Your turbine pump is that is not changing, I should say. You're pretty much changing the brand name. Okay, so even and the reason for this, why we probably wouldn't need a permit for it, is because even if you have the same brand and it comes off the same line, an hour later or something, there is still a good likelihood that will be, have some variability to it, whether it's a couple % or not. So even if it's the same brand, same assembly line, things like that, it can still theoretically be different. Okay, so we probably would not balk at that too much. It's pretty much replacing like for like. Okay. Now, on the other side of this, replacing a 400 gallon per minute brand X line shaft vertical turbine pump with a 400 gallon per minute brand X submersible pump. Okay, this is definitely a change. This is changing the configuration of your well house. This is changing the configuration of just how the water in general is pumped. Okay, so this would absolutely require a permit. You should absolutely submit a permit for that. Talk to your district engineer to get it in place. That last bullet point there. Replace well house turbine meter with a mag meter. I would just say no. You're not changing the configuration. You're not changing the capacity. You're not changing anything like that. It's just a meter for meter replacement. Nothing. It's too minor to really have an issue on our end. Okay, so project management, planning, design, permitting, construction. Basically the biggest thing I want you to take away from here and during this process is as an operator, in charge, or just an operator of a drinking water system, you should be aware of what's going on. Okay, as I talked about early on, this is something that you're mainly overseeing. This asset management plan, this capital improvements plan, things like that. These are important, and it's often overlooked. A lot of these things are, out of sight, out of mind for the city council, the village president, whatever the circumstances is. So a lot of that responsibility, whether that's right or wrong, probably falls on the operator in most circumstances. So you should be very familiar with what is going on with the project, whether that's the initial planning, being the one that's trying to get that money for that system to maintain that system or upgrade that system, whether that's during the design process itself, if you're working with a contractor, if you're working with the city engineer, things like that, you should be in the loop. The operators should be in the loop. They should know what's going on. Okay, and they should have a good idea. If they see something, even during the permitting process, like, oh, that doesn't make sense, or that's out of place, or where's the thrust restraint here? Even if you don't understand, your engineer should be able to point that out pretty quickly to you, or help you out, or realize that they made an error, right? So these are the things. Make sure that you're staying involved in all aspects of this. Yeah, you're one of the primary pieces that is looking after this your distribution system, your drinking water system in general. Okay. So water main installation, and we're going to kind of go through each one of these points, but there's a few trends here, just in general, but there's preparation, excavation, and then, the actual laying of the pipe. So gasket lube, so it's important for that short-term purpose, but then that pipe bedding is good for that long-term purpose, right? Okay, that pipe bedding is going to be what keeps that water main intact for a long time, so you're not having flexing and joint failure and things like that. Okay. Making sure you have adequate physical and sanitary separation from things, whether that's vertical or horizontal, whatever that is. Make sure that you're flushing, getting the large chunks out, getting that debris or whatever during that process out, right? Then you're doing your leakage and your pressure testing. Don't rush this portion. That's, highly suggested because it's the long portion, and make sure that you're doing it right, and make sure that the water main was installed properly. And if you're not failing, or if you're failing that test for whatever reason, it means it probably wasn't installed properly, or something went wrong along the way. Okay. Then you're going to go through that disinfection portion, having that chlorine installation, or that chlorine, addition or whatever, to make sure that it is sanitary conditions in an improved method that we'll talk about in a minute. Flushing again to get rid of that or to distribute that chlorine through the water main to make sure that it is adequately chlorinated through and through. And then going through and doing your back T testing. In general, I'm just going to say 2 consecutive samples, negative samples, 24 hours apart, right? Should be at every 12-inch or 1,200 foot interval, and should be at every branch, every end of the water main. Okay. And then, lastly, doing that final flushing until normal residuals are met. Okay. So that's just the general overview, but we'll cover these in more depth in a moment. So excavation and preparation. What I'm going to say right off the bat is most of these are pretty much catered towards or focused on basically safety, right? One thing is destroying or disrupting other portions of your whatever infrastructure in general, but most of this is focused on safety, whether that's your own personal safety, other operators' safety, or the your residents themselves. Okay, so general preparation, call, miss, dig. Make sure you're not tearing up a gas line, electrical line, whatever, expenses and safety concerns there. Excavate the plans. Make sure you're meeting the plans the way they're drawn up. Shore up the trenches. Make sure you're not having those cave-ins. Store soil away from the trench. Again, kind of driving that point home. Making sure that you have true trench safety, especially if somebody's getting down in that hole. Okay. The width of trench, making sure it's adequate to the soil type itself. Making sure you're having proper depth of trench. Maybe there's trench boxes if necessary, depending on the situations. 18 inches from center line or 1 foot on each side of the pipe for that width portion. Again, somewhat dependent on what you're dealing with for soil conditions and things like that. Okay, the other, the right side here, ensure stable foundation. Again, everything's important, everything's safety related. Make sure you're being smart, make sure you're being safe. Everybody's life is important. We don't want to, have somebody get injured because we just we're trying to rush something, or didn't think something through, or that it goes into that the old adage of slow is smooth and smooth is fast, right? Okay, so it might seem like a lot to go through this safety precautions, but it will save you time in the long run, especially if things go wrong. Okay. Separation, whether that's physical and sanitary, concerns there. 18-inch on vertical. So if you're having those water main crossing with something else, making sure there's at least an 18-inch vertical separation there, and then 10 feet horizontally from something, whatever the utilities are. Okay. And then centered pipe joints at crossing. So what that's basically saying is if you're going through a crossing section there with whatever, say it's a sanitary sewer or something like that, making sure that those joints are as far away from that crossing as possible. So you're trying to center that out. Okay. Rock excavate extra 6 inches of rock and backfill with clean sand. Okay, making sure that foundation is solid, and then dewater as necessary. Okay, so pipe storage, make sure the covers the ends are covered. Make sure that they're cleaned. And there's not too much debris getting in there. As you can see from these, they're probably pretty inadequately stored opportunities or water mains here. As you can see in that second picture I just pulled up, there's some form of a larva or bug, whatever's going on there, just hiding under that gasket. So again, making sure that stuff's clean, because as soon as you get it in the ground, yeah, you can do flushing or whatever, but sometimes flushing doesn't get all those things, especially something like this, a bug inside of a gasket. If you didn't clean out that inside of the, brush out that inside of that gasket, maybe that's you're going to be getting back teas for the next, couple of months or something until you tear that water main back out or something, or chlorinate enough to get it done. Okay. So handling and laying pipe, obviously inspect for damage, inspect for cleanliness, handle that pipe with care, especially if you're talking, ductile iron pipe, make sure you're not disturbing that mortar lining, things like that. Laying the pipe, lowering it in the trench by hand or mechanical equipment. It's recommended that you put the bell end in the direction of it laying. So you're putting the bell end towards the direction that you're continuing to work towards. Okay. That's just pretty common practice. And then keeping debris and soil out of the pipe. That means capping that end at the end of the day or whatever in some fashion, or just going through it as you're doing that process in general, making sure that they're maintaining a clean, fairly dirt-free installation. Because as we, I'm sure, have all experienced at some point in time, you don't want to have continued bacteriological issues. So pipe bedding, we've talked about this quite a bit, but in general, you're just making sure that trench is level, make sure that bedding is adequate. Okay, making sure that it's that clean sand. Okay, it supports the whole length of the pipe, right? If it has those bell ends, right, maybe you're creating, little pockets there. What we typically call them bell holes, right? It relieves that undue weight. That's where that stress would normally be on if you just were lay that bell end flat. Okay. So maybe giving a little bit of relief at those portions. So the majority of that pressure, majority of that weight is directly on the pipe wall itself, not necessarily the less structured bell end of it. Okay. Approved, pipe lube, making sure that it's NSF approved. You're not using, food grade things necessarily, whether it's lard or vegetable oil or Crisco or something like that, making sure that is an approved method that does not support bacteriological growth. That's again, a big one. And this specifically is water dispersible. The picture that's on the screen there, that can be important, as you're talking, putting it in the ground. So if you're dealing with a river crossing or something like that, you might want to have non-dispersible because it might, wash away that a little bit faster or something like that. So keeping those things in mind, so those spigot ends slide smoothly into that bell end. All right, things to consider. Okay, so backfilling, again, making sure that you have a good base to start, you have that water main lined up, yeah, everything like that, and then making sure that you're Use only clean sand or soil for the initial layers. Make sure that it's free of stone, debris, peat, roots, frozen materials, etc. You want to have a good base so that water main isn't flexing and moving all that much, right? Having a really solid, it's not getting damaged by, crushing pressures or something like that. Then your first layer backfill, install the material up to the center of the pipe, and keep the joints exposed until after the pressure, testing is complete. Then compact it, compact the actual, that backfill material around the pipe with either with hand or a pneumatic tamper, something like that. And then continue adding layers of good quality backfill and continue to secure the pipe. Okay, so as you kind of go in layers, you're going to go every, the final layer should be at least 6 inches above the top of the main there for water mains that are, less than 8 inches. Okay. Thicker layers may be required for larger piping, depending on the situation, or at least they're recommended. Okay, so you're having good compaction, again, keeping that water main as well intact and in place as possible. And then you're filling the rest in with the excavated material, and then you're going to compact. And it's advised to wait until the pressure testing is completed, and then you can go from there. Because if you have to dig that all back up, it's probably not worth it. Okay. Thrust blocks, we've already talked about these a lot. So all depending on making sure that you're meeting those requirements there. Now there's a lot that goes into thrust blocking, and we'll kind of cover this. So this is just some different examples, different for the different fittings that you might have, whether it's elbows and things like that, all in the direction of thrust that are most important. And the design and structure of the thrust blocks are obviously very important, and have different designs for different circumstances. So thrust restraint, obviously we all know that water moves at a lot of, has high pressure, maybe has a lot of velocity and things like that. And when those things change, we can have things like water hammer, right? Excessive amounts of force being released into a certain direction or into a certain area. If that's on a joint or something like that, that's not mechanically restrained or not thrust, have some sort of thrust restraint, we can have serious issues, whether that's rupturing or a breaking or a pull out of the joint itself. Okay, so we need to make sure that that thrust is there. And we've already kind of talked about some of these things already: thrust blocks, restrained joints, proprietary fittings, things like that. Okay, to really control that pressure in place. Did I just skip to? No. Okay. Thrust blocks. So made of concrete or steel rods, cast in concrete. So it's all kind of depending on the situation that you're doing. Rests have been undisturbed earth. Again, we already kind of just talked about that, making sure that pressure is being released into that compacted soil to disperse it as best as possible. Standard engineering formulas are used to determine the size of the actual thrust blocks themselves. They should be centered in line with thrust force and cradle the fitting. Okay, that's a big one. So not the joints themselves, but the fitting itself. Make sure that fitting doesn't move. The fitting doesn't move, then the joints won't move. We don't need to focus on the joints because there's more chance for error. We need to focus on the fitting itself. Make sure that fitting doesn't move. Okay. And also installed under hydrants and gate valves as some other fittings, things like that, rather than just elbows and Ys and things like that, crosses. Okay, so this is an example of DIPRA, the Ductile Iron Pipe Research Association. This is out of one of their manuals. This is just a quick guide on what you expect on the size and things like that under certain conditions. Now, there's DIPRA has a bunch of tables in their manuals. What I will say, especially in this modern day era, they also have an online thrust block calculator. It's actually pretty cool. I highly recommend checking it out. Go on the DIPRA website and look up thrust block calculator. You can set it to a bunch of different conditions, bunch of different sizes and dimensions and fittings and whatever that you need to do, and it'll give you the result and kind of give you a little diagram as well with it. It's actually pretty neat if you like that stuff. This is obviously that mega lug. We've already kind of talked about this. You have these these screws here that's actually pinching down into the pipe, keeping that in place. So again, just another method to, dissipate some of that thrust. And obviously, maybe one of these won't work, so you should continue that down the line until all the thrust is dissipated in that length, similar to what we talked about earlier with extending that length of water main. Okay. So a few things are going on here in this picture. You have this, mechanically restrained portion here with these rods. You also have a slip joint here that we had mentioned earlier. So that's that, outer piece of piping here that there's probably a gap right in here. And then you have, it's tied together with the two, gaskets and features right there. Okay. Truss or coupling, slip joint, whatever you want to call it. Okay, so flushing, getting into that flushing portion. This is a big portion for maintaining sanitary conditions, right? So maintaining that 3 feet per second, that's kind of the new, kind of the common standard these days. Getting that scouring velocity up, right? You don't want it too high, but you don't want it too low either. You want to make sure all that, debris, dirt, sand, things like that are getting to a high enough velocity that you're actually getting it out of the main. Okay. Flush, and it's recommended that you flush long enough to remove 2 to 3 times the pipe volume of water. Okay. So flushing, a little bit flushing guidance as per an AWWA standard for disinfecting mains. That's C651 that you can see on that picture right there. This is an actual table from that. But obviously you can do these calculations on your own as well, but this is just kind of a little cheat sheet that you can do, based on certain PSI, things like that. This is what you should expect given a certain pipe diameter, what you need to meet for the gallons per minute to meet that 3 feet per second. Okay. But it's fairly, easy calculations as well that you can do on your own. So going into the pressure testing portion of that. Okay. So you've installed the main, you've flushed out the main. Now you're getting into that pressure testing. So there's kind of a whole process to it. Obviously, there's a lot of AWWA standards that you should follow, and we'll get into that. But for just general terms, minimum test pressures are a little different depending on if it's ductile iron pipe versus PVC. So 1.25 times the working pressure at the highest elevation of pipe. And 1.5 times the working pressure at the lowest elevation of pipe. PVC is similar in that regard. It just doesn't have that lowest elevation requirement. Okay, so it's making sure that those internal pressures are adequate, making sure that and as you're doing that pressure testing, there's also a leak testing that goes along with that. So what the pressure testing it really gets into is essentially you're pumping at that minimum test pressure, whatever you're setting that at whatever that minimum is. Okay, and you're doing that for 2 hours. During that time frame, the test pressure, shall basically must stay within plus or minus 5 psi at all times during that 2-hour test. Okay, and then as well, because you're kind of doing this at the same time between the pressure testing and the leakage testing, make sure that you're measuring the amount of water used to maintain the test pressure for the entire 2-hour period. Okay. Next slide kind of gets into this and kind of shows us, actually the next 2 slides describe this a little bit better, but essentially you have this water main here. Obviously you're doing your test pressures here, you're doing your leakage testing. You have whether that's a calibrated barrel here that's holding water, and or you have a meter or something that's actually measuring the amount of water that's being pumped into this. And then you have a pressure gauge that's telling you that you haven't gone plus or minus that 5 psi during that time frame, right? So you're pumping it out into this main, and hopefully it's staying fairly stagnant, within plus minus of 5 psi, and then hopefully you're not losing a bunch of water, because that just basically means that there's something going wrong, whether that's a gasket didn't seal properly, or one of the joints is failed, or maybe there's a hole already in the pipe, depending on whatever the circumstances. Okay. This is just a real life example of that. So you have your tank here. It doesn't look to be, calibrated to any sort of volume. But what it does have, it has this pump here, but what it does have is a meter here and a PSI gauge. So you're getting both, both items here addressed as you're going through that process. Okay, both leakage and pressure testing. So leakage formula here, I'm not going to get into the details of that, but that can also be found on one of the AWWA standards, okay, depending on what you're using. But that's the equation. Okay. So disinfection of the water mains. This is the last step before placing the main into service. So you're flushing, you're disinfecting, testing for bacteriological, and then you're basically good to go before making that final connection. So disinfecting the water main, C651 that we already addressed. This is the standard. I think it's -14 if I'm not mistaken. It's the most recent version of it. So this is there's basically 4 approved methods of chlorination. Obviously, you can go through that methodology or that guidance document that's part of the AWA manual to really walk through each method, make sure you're doing it properly. This is just a general overview. So methods should be kind of selected based on the length and diameter of the pipe and or the material and equipment required. Okay. Please note that for some of these, dechlorination may be required. So you're not just dumping chlorine, high concentrations of chlorine water, just downstream or something like that that might affect the local ecosystem, or environment, whatever that circumstance is. And make sure you're meeting that standard C655 to make sure that you're dechlorinating properly. But those are the 4 test methods on the right there. There's the tablet method, continuous feed method, slug method, and then the spray method. Okay, all technically valid given this whatever circumstance. So continuous feed method, basically fill the new main with potable water that has at least 25 milligrams per liter concentration. Hold for 24 hours and measure residual. Valves and hydrants should be operated during the holding period. This should be pretty common practice for any of those methods, by the way. You should be obviously operating those valves and or hydrants as you're kind of going through that process of the chlorination portion. So that chlorine residual must be at least 10 milligrams per liter after that 24-hour period. So you're starting with that 25 concentration. If it decreases below that 10 milligrams per liter concentration, then you're going to have to do it again. Okay, you're going to then flush, make sure that that chlorine residual goes back down, and then do your sampling for coliform. Okay. So the tablet method, you're taking 5-gram tablets of 65% chlorine. You're going to basically tape them to the top of the water main to obtain roughly a 25 milligram per liter concentration. The tablets should be placed upstream, should be placed on the upstream end of the first section of pipe, each branch main, and every 500-foot intervals to again kind of maintain that chlorine residual up of 25 milligrams per liter. Make sure that that tape is NSF 61 approved, and then you're basically going to be slowly filling that pipe, and then you're going to wait 24 hours. So make sure that those chlorine residual or those tablets relatively stay in place. So you're filling that pipe very slowly, not washing them all down to the end. And then you should have a detectable chlorine residual after that 24-hour period. And then as the norm, you're going to be flushing and then doing coliform sampling after that. The slug method is, obviously a little bit different here. You're going to be moving a slow slug of highly concentrated 100 milligram per liter chlorine water through the water main at a very slow rate, right? You're going to be basically exposing that water main to this really high concentration of chlorine. Again, operating those valves, operating those hydrants, things like that. You need to be measuring that chlorine down the line, and that should never drop below 50 milligrams per liter. If it does, you're going to have to go back to the start of the slug, chlorinate back up to 100 milligrams per liter, and then keep going down. Okay. And then again, per usual, flush and do coliform testing. So dechlorination, as we talked about, making sure that we're looking out for the environment and keeping maybe some potential other eagle staff, off your backs, if you will. So dechlorination, high chlorine levels, especially maybe that slug method would be a good example of that. So maybe you're using some other compounds, whether it's ascorbic acid, sodium thiosulfate, or hydrogen sulfide. Okay, and the same should be true, although we're talking about water mains here, the same should be true for storage tanks as well, or anything else that you're chlorinating to a really high level and then trying to flush. Okay, so and then bacteriological testing. So basically, it's making sure that you're meeting sanitary measures. Making sure that once you put that in, back online or putting that in line with the actual distribution system, the water system in general, that you're meeting those standards, making sure that we're not going to have potential for health hazards later down the line. Okay, so sample sites every 1,200 feet, and at the end of the pipe, as well as any branch that might be part of that water main project. Okay. And then, general rule of thumb, although this is changing, is 2 samples 24 hours apart. So this is why I'm saying, there's potential that you can do something else. There's other options here for doing bacteriological testing. Act 399 specifies 2 samples 24 hours apart. That's pretty much the normal. It's really easy to remember, in my opinion, easy to say, but there's also that opportunity for another alternate approved method. Okay, and Eagle has already come out and said that we accept the AWWA standard C651 options as well. And so there's 2 different potential options there that come from bacteriological testing. So there are bullet points 1 and 2 right there. So collect the first sample, wait 16 hours, then collect the second sample. Or you could wait the 16 hours, take the first sample, wait 15 more minutes, and then collect the second sample. Again, general rule of thumb, 2 samples 24 hours apart, but theoretically all 3 of these are valid options if you specify them ahead of time. Bacteriological testing, flushing is not allowed in between the collection of the 2 samples, so make sure that you're getting that actual representative sample there. It should be sent to a certified lab as per Eagle requirements. And then all samples must be reported as negative for total coliform bacteria. Okay, before making that connection to the existing system. So I hope you understand that the whole reason we're taking bacteriological samples is to make sure the water is safe. Hopefully you wouldn't put together a water main if you didn't know that was a safe condition. Okay. And then final connections with the existing main. Main appurtenances used to make the final connection to existing mains must be flushed and disinfected and then sampled, right? So make sure that those pretty much the same kind of concept. For connections less than 1 pipe length, so less than 20 feet roughly, may be sprayed and swabbed with a chlorine solution for that disinfection purposes, right? And then connections greater than that 1 pipe length, you should be setting them above grade, you should be disinfecting, you should be sampling, kind of the same sort of way. Then after those samples come back, then you can make that connection, make that installation. Okay. Repairing breaks or leaks. So if you have a water main break here, depending, all the system or all the situations can be different. So if it's a small one, hopefully you can do that without depressurizing the system. Maybe you're, decreasing the valve, you're closing the valve slightly just to decrease that pressure a little bit. Maybe you're just putting a simple clamp on or something like that. No big deal. Okay. Maybe larger in size, maybe you actually have to isolate using valves. You might have to dewater a trench and then, disinfect that localized area. Okay. And then if there's a major repair, you should be going through that whole process again, that pressure testing, flushing, disinfecting, and then sampling again. Okay. And this is an example of just like a, pretty simple, repair there. You have clamps, things like that. Looks like potentially, that almost looks like a slip joint, that one in the middle there. So that's, pretty standard issue, methods for fixing an issue with the water main. Okay. Cutting in sleeve is basically just, kind of, in my opinion, I think they're kind of similar to like a slip joint there. Basically this portion here between this one and this one are sliding. So you're sliding this over to one side, and then extending this piece out to whatever is necessary to make those connections. So emergency disinfection, each event is handled case by case. If you start having issues or bacteriological issues or whatever, you should absolutely be contacting Eagle immediately. There is that requirement there that you need to contact your district engineer. as well as making sure that if you're going to be going into a boil water advisory, make sure that you're hitting some of the larger aspects there. Some of those, whether it's a medical facility, food establishment, probably contact your local health department to kind of help you out with that as well. They can get a list to you pretty quick of those potentially high risk locations. And then obviously you're going to be going through this bacteriological sampling. Okay. Distribution system valves. So, flow control, isolation of breaks, air relief, prevention of flow reversal, and others. So there's lots of reasons to use a valve in a system, any given system. So, they're fairly crucial in a lot of circumstances. So valve spacing should minimize system disruption during repairs. So, the general rule of thumb, if you say have an intersection and you have, four, the water main is going in 4 different directions, northeast, south, and west, let's say, you should at least have the number of valves that's, less one of that connection. So if there's 4 connections there, you should have at least 3 valves, because that will give you the opportunity to isolate any given main that's necessary, whether that's closing all 3 valves or whether that's just closing one to isolate that portion of that. Again, minimizing that disruption to the community. Okay. And potentially isolating an issue as well. Okay. So, and then typical spacing there, commercial areas, maybe you're talking every 500 feet, residential areas, you're talking about every 800 feet. And then maybe if you're talking large transmission mains or something, maybe it's a quarter mile, half mile, maybe a mile, depending on what the situation is. So just, again, things to keep in mind as you're going through and building your water system. So service lines and pipes, basically service line is that connection from the water main and delivers that water directly into the home. Okay, so typically you're talking about 3/4 inch to maybe somewhere up to 1.5 inches is probably a pretty common sizing. Business and industries may be a little different, depending on, especially if they have fire suppression, things like that, maybe can be much larger, or if they have some sort of water usage in general, depending on what that process might be. Okay. Okay, service line installation. You have your corporation fitting, that's the actual connection to the water main. You have that gooseneck potentially, or that bend in a piece of piping. Maybe it's a change of material or not, that's somewhat dependent. You have a few things there. Maybe it's a curb stop, maybe it's a curb box. And then, usually at 5 to 7 foot burial. And, and then it would run inside the home. So especially for DSMI purposes, the distribution system materials inventory, you're all probably going through that and making those notes on what your service line materials are. So that's that water main to that first 18 inches or first shut off valve, whichever comes first inside the house. Okay, that's what comprises your service line. Corporation fittings or corporation stops basically is that connector piece that takes the actual service line material and connects it to the water main. So it's tapping that. Maybe you're using a saddle in certain situations, depends on what materials your water main is, depends on what materials your service line will be. Okay. Now, corporation fittings, as you can kind of see here, there's different style. There's basically 3 different styles of threading that can occur in any given style of piping. Maybe not necessarily just corporation fittings, but corporation actually has a very tapered fitting. This is, typically it's probably commonly referred to as a Mueller thread. Just again, that's a brand name, but that's typically for your tapping portion of that. It's this very tapered, kind of thread that taps into the main. Now there's also a few others, MPT, which is your national pipe tapered threads. It's also tapered, but maybe not as much, as a corporation fitting here. But then you also have your straight fitting, your straight threading as well, which is your NPS, your National Pipe Standard threads, which is basically your straight cut. It's a straight across thread. That's where you're gonna get like, electrical hardware and things like that is going to be, similar to that. Okay, so make sure that your threading is proper as you're going through those process. So service line materials, again, kind of rolls into the DSMI a little bit here. Commonly we have copper. Copper's been around for a long time. We're still using copper. It's a good material. It's durable, holds up real well. Type K copper is probably the most common. You also have plastic, whether it's PVC or HDPE, things like that. That again have proven to be pretty solid materials overall. Not a whole lot to really say about that. Most of you should be pretty familiar with service line materials. So service line materials that are no longer installed. They might exist in your system anymore, but you shouldn't be installing them anymore. Well, obviously, lead's a big one. We're trying to get rid of all the lead. And then, as part of your lead service line replacement program. And then you also have galvanized. Galvanized is, just not a great material to begin with. It's common to have heavy tuberculation, as you can see in that lower picture right there. And it can harvest and it can hold, lead particulate, which can release in large quantities and create another health hazard as lead does. But yeah, no longer in use, or no longer being installed, I should say, potential that they are in use. So that also falls into a little bit of the DSMI portion for you. And then service line taps. So you can have a dry tap or you can have a wet tap. So basically dry tap means that there's no water in the line. It can be done with or without a saddle connection. Okay. Wet taps are typically done under pressure. So there's water in that line and it's used with a tapping machine typically. So basically you're making that cut into that main and you're putting that corporation fitting on basically at a similar kind of time. Okay. Where the dry tap is probably done, in kind of a succession kind of style. So you'd be cutting, and then you'd be either putting on the saddle or tapping directly and then making those connections. Okay. Curb stop and box. So typically installed at the property line, although that can depend from community to community. Basically just provides a way to easily shut off, the curb stop valve. Okay. Pretty straightforward. You use your curb stop wrench to take that cap off, run it down the hole. Hopefully it's intact and there's not a bunch of debris in there, so you can easily get to the valve and make that quick turn. Okay. This is just an example of a service line. As you can see, you got your corporation fitting here, you got your water main. Maybe there's a little bend in the pipe here, whether that's an actual gooseneck, the actual change of material or not. It's hard to tell, I guess. But it looks the same material. You're going to the curb stop box here. Now this actually says the property line's over here. Obviously, that's somewhat dependent on any given community and things like that. And then you got your meter and your gate valve out here, but then your first stop waste valve is in here. So depending on where that 18 inches is, looks like this is probably going to come first unless 18 inches is somewhere inside of that. Okay, so just an example of that. Here's another example. Here's your water main corporation fitting runs down. Your meter's actually outside of the home. So a meter box here. I would say that this is not ultra common in Michigan just because we do have maybe potential freezing concerns here, but they do exist from time to time. But yeah, pretty straightforward, I'd say. And that's the stop point, and that's the end of my lecture.